All right. Electric fields. This is section number 5, I believe. I've got the key up here because it's a lot of definitions at the beginning, so I'm just going to show you the key and talk through the definitions really quickly. Explain what gravitational field is, what causes a gravitational field. So you know that gravitational field is an effect that exists in space where objects with mass exert gravitational force on other objects that have mass. So for example, I have mass, I exert gravitational force on every object around me, I exert it on every single student that sits in my classroom, my students exert it all on me, right? That's gravitational field. We define it as G, and it's represented either with newtons per kilogram or meters per second squared, depending on how you want to represent it, okay? Whether it's acceleration or the force due to gravity, but it's the same number either way. It's the amount of grav force exerted by each kilogram, or on each kilogram of mass in a grav field. So for every kilogram of mass that I have, I get this many newtons of force applied to each kilogram of mass that is in that gravitational field. And well, I'm entirely in the gravitational field. There's two different equations that we have, which is G equals gm over r squared. That's for gravity created by an object. We learned that last year towards the end of the year, I believe, with gravitation, okay? And then there's also force of a G field, which is our traditional mg equation, or weight, right? Electric field, there's a lot of parallels between electric field and gravitational field. They're very, very similar in a lot of different ways. The electric field is the effect in space created by objects with charge and exerts electric force on other objects with charge. So you know that gravitational field is created by objects with mass and exerts force on other things with mass. Electric field is created by objects with charge, and they exert it on other objects with charge, okay? We define electric field with the symbol E, and the units are newtons per coulomb. It's the amount of force exerted on each coulomb of charge in the E field. So it's the same definition as gravitational field, but we replace it with more relevant words, right, for E field, for electric field and all that fun stuff, right? Okay, and then finally, the symbol in units for electric field. So, I talked about that up here. But the equations that we have is that if a charge Q creates an electric field, it's going to have a strength that is equivalent to KQ over R squared. And if you have a force that's exerted on a charge by an E field, you would just use Q times E. So again, you can see the parallels really, really clearly, okay? And it's pretty straightforward, right? Okay, so if you flip that page, it'll take us to a couple more definitions and such, right? The gravitational field near Earth's surface we've talked about before is 10 either newtons per kilogram or meters per second squared, okay? And that means that every kilogram of mass in the gravitational field receives 10 newtons of grav force. Okay. The electric field near Earth's surface is approximately 100 newtons per coulomb. So that means that every coulomb of charge, okay, receives 100 newtons of electric force. Okay. Now, do you need to know that 100 newtons of electric force gives you that? No, not necessarily. It's not really a constant that you need to memorize, but it is kind of fun to know. I don't think you need to know it. Let me double check really quickly. It's not it's not on your formula sheet, so I would say you probably don't really need to know that, okay? But, yeah. Okay, electric field strength inside of a conductor. So inside of a conductor, okay, it's 0. In all conductors, okay? Because the conductor is, it kind of polarizes, right? Okay, the conductor polarizes. So the charges, what happens is on the surface of the conductor, the charges move around due to the E field. Okay. Around to the E field until there is no more E field inside. Okay, so the charges move around to basically cancel out the E field in the inside of the conductor. Okay, there's a boundary condition for electric field. So if you have at the surface of a conductor, the E field always points points perpendicular. To the surface. Okay, you might hear the word orthogonal. Orthogonal also means perpendicular. Okay, normal does as well. Okay, so if you have E field always points perpendicular to the surface, so it's like if you have a sphere, right, the E field is always intersecting at 90 degrees with all points on that sphere's surface. Okay. Okay, a person of mass m stands in a special chamber built to create an electric field. The floor has negative charge, ceiling has positive charge, giving the inside of the chamber electric field E. Person carries a net charge Q. So the person is charged. What direction does E point in the chamber? Okay, well, we know it's got to go down, and I'll tell you why that is, okay? It's got to go down because it goes away from the positive and towards the negatives, okay? Remember we kind of did this in circuits, right, where the charges left the battery through the positive terminal, they went away from the positive and then went back to the negative, right? That's going to be pretty much how that kind of works out, right? Okay. So the E field should be pointing down, okay? Now, if the person, suppose they enter this chamber and they get lifted up by the electric force, they would have to have a negative charge. The reason is, and you can think of this in two different ways, okay? The reason is because they want to be repulsed from the negative floor, okay? So they're going to enter and the bottom plate is going to repel them, okay? So he's going to go up into the air, okay? You could also think of it as the positive ceiling is attracting him too, okay? But another way to think of it is that negative charges oppose the flow of electric field. And we will talk more about that later. But just so you know, negative charges do oppose the field, okay? If mass is 100 kilograms and the field strength is 3 times 10 to the 6th, what charge must the person have to be lifted up? Well, first off, if we drew a quick free body diagram of the person, you would notice that he has gravity going down and electric field going up. So if he's floating, right, these two are going to balance each other out. Yes, maybe the electric field was stronger initially to go up, but eventually he gets further and further away from the bottom floor, which would actually cause the electric field to get a little bit weaker. I guess that's one way you could think of it. But I would say that when he gets up to this point where he's at equilibrium and just floating, he's not going up or down any, he's just floating, then these two forces balance each other out, right? So you would say that the electric force is equal to the gravitational force, okay? So you would get QE is equal to mg, and then you would plug everything in. We don't know the charge, that's what we're trying to find. E is 3 times 10 to the 6th, okay? The mass of the person is 100 kilograms, and G is 10. We're just going to use 10 just to be simple here, okay? And if you solve that out, you should get that Q is equal to 3.33 repeating times 10 to the negative 4 coulombs, okay? Which is approximately 333 microcoulombs, okay? I'm never coming here again after hours. This is terrifying, okay? Okay, the Millikan oil experiment example. If you were here in class when I did it, you'll know that I got it like horribly wrong, and I did redeem myself, but you can kind of thank Ms. Zancho Palmer over at Walnut Grove for helping me get back on the right track, okay? This example is about an experiment that Robert Millikan did back in 1923. I was there for it. He took an atomizer, which is a little device where you can take one or more electrons away from the oil. So he put oil into an atomizer and he sprayed the oil, okay, into this region between two plates that were charged with a voltage source, okay? And so what happened was what he would notice was that he saw all these little oil droplets floating between the two plates, and he was able to then use this to determine the charge of a single electron, okay? So he built two parallel conducting plates, okay? They were connected to a voltage source, so they established an electric field, and then when he sprayed the oil into it, it was floating, okay? Each of the droplets have the same mass, which is just big M, okay? And the oil droplets, they're floating, right? So first off, we need to figure out In which direction must the electric field point? Well, actually, first off, we can figure out the charge of the atom of the oil droplets, right? Because guess what? If you're removing an electron, what kind of charge does that give you? Yeah, makes it positive, right? Because you're taking away an electron, right? So now you have more protons than electrons, okay? So then if the oil is positively charged or has a net positive charge and is floating, which plate must be positive, which plate must be negative? Okay? The bottom one would be positive, okay? And the top one would be negative, okay? Okay, same logic as the guy in the previous example, right? So if we remove electrons, then the droplets have to be positive, okay? Electric force must point up to balance mg. So E force must point up to balance mg, okay? If E field goes positive to negative, okay, so up is towards negative. So the electric field's going to go like this, okay? Okay. So then if we drew a free body diagram for the droplets, you would see it would have mg going down and it would have the electric force going up, okay? Okay, the data is provided here. This is the data that Millikan obtained in the experiment, okay? This is it. Yeah, I was there, right? I helped him write down the data, okay? He didn't credit me when he got his Nobel Prize. I was very sad about that. Okay, so Millikan, he gets this data, and you notice these gaps in here, right? So the important thing to note is that each of these gaps represent different levels, different electric field strengths and different levels of charge, right? So notice that there's little clumps in the graph, right? We have a clump right here, clump right here, clump right here, right here, right here, and right here, right? These are clumps in the graph. Each of these clumps actually represents how many electrons get removed. So if you only remove one electron, there you go, right? This data represents the electric field strength if only the electric field strength and the charge if only one electron is removed, okay? This one represents if 2 electrons are removed, okay? And 3, and 4, and 5, and 6, okay? So we can see now, you know, what happens, right, as we remove electrons, right? You'll notice that the electric field is getting stronger and the charge is decreasing, or the net charge is decreasing, right? Because, you know, if you have 6 electrons and 6 protons, the net charge is 0, right? So there has to be a charge here that we end up getting, right? A net charge, right? That's what that is, okay? But it's important to note that why do we have these gaps? Why is the data not continuous here? Well, you may have remembered that last lesson we learned about a word called continuous. Maybe it was the one before. We talked about a word called continuous and discrete and quantized, right? Charge is quantized, okay? Which means that you cannot have anything other than whole electrons, okay? So that means that what's happening, right, you can't take away half an electron, you can't take away a quarter of an electron, you can't take away 3/4 of an electron, you have to take away one whole electron every single time. So he could only take away one whole electron every single time. He can't take away half of it, he can't do whatever, right? He has to take away one at a time, okay? So to figure out the mass of the oil droplet, right? To figure out the mass of a single oil droplet, we would again use the principle that QE is equal to mg, okay? But this time the charge is going to be a little bit different. We're actually going to use data from the graph for this, because so what we need to do is we need to figure out charge and E field, okay? Mass we're not going to know, G is constant, right? So we'll just write this side of the equation because we already know what it's going to be, okay? But the left-hand side, we need to figure out the charge, okay? If we take 6 electrons away from it, if it's a neutral object, we take 6 electrons away, then how many protons are in excess, right? 6, right? Because what's happening is if you initially have what, like 12 electrons and 12 protons, and you take 6 electrons away, well, how many protons are in excess now? 6, right? Because you have 6 electrons and 12 protons, so 6 are in excess, right? So it's actually going to be 6 times the elementary charge. 6 times the elementary charge, 1.6 times 10 to the negative 19. And the E field that corresponds with if we take away 6 electrons away is 500, okay? And then we just solve to get M. M equals 6 times 1.6 times 10 to the negative 19 times 500 over 10. You're going to get a really big number, okay? I think, I'm trying to think, in the key I don't have it. Oh no, the key, sorry, I've got it right. It should be about 5 times 10 to the negative 17 kilograms, okay? That's a really, really small amount of mass, and as expected, right? It's an oil droplet. It's not that massive, right? Okay. Good on that one? Great on that one. All right, cool, let's move on. Okay. Determine the electric field magnitude and direction at point A in the diagram. So here's something important to understand is that when we figure out the electric field, right, if we're considering it with reference to a neutral point or just like a random point in space, all we got to use is that equation that we talked about, E equals KQ over R squared, right? Because there isn't a second charge to consider, okay? So all we got to do is just use that version of the equation. One thing that's important to note is that for neutral objects or for points in space, okay, objects, for a neutral object or for a point in space, okay, positive charges repel. They emit a repelling force, whereas negative charges emit an attractive force, okay? So if it's a positive charge acting on an empty point in space, then the electric field is repelling from them. But if it's a negative charge acting on a point in empty space, then it is a attractive force, okay? And you'll see that a little bit more when we talk about electric fields, okay? So let's take a look at this. Let's take a look at each of these little charges here. I'm going to circle them in the colors that I'm going to use to represent them because I'm colorful and fun like that, okay? Okay, let's take a look at charge number 1. What's the E field that is created by charge number 1, or the one in green, okay? It's going to be K, which is 9 times 10 to the 9, times Q, which would be, you could do negative, you could drop the negative, doesn't matter, negative 1 times 10 to the negative 3rd, over R, the distance between this and the point we're looking at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And you calculate that out, you should end up getting 90,000 newtons per coulomb to the left, okay? Okay, you get 90,000 newtons per coulomb to the left, okay? And it's pretty straightforward, right? Nothing too crazy. And you don't need to include the sign as long as you include the direction, okay? Okay, what about for number 2, for charge number 2, E2, okay? 9 times 10 to the 9th, okay? Times 36 times 10 to the negative 6th, okay? I'm so sorry, I completely forgot to explain this, right? So notice that we changed charges here. This is a millicoulomb, this is a microcoulomb, right? So this is now times 10 to the negative 6th, right? This is times 10 to the negative 6th. Okay, that's micro. That's in the SI prefixes that are on your formula sheet. Micro right here is mu, 10 to the negative 6, okay? Okay, and the distance between A and that is just 3 meters, okay? And then you would calculate that out to end up getting 36,000 newtons per coulomb to the right, because it is a positive charge and it's repelling from that point, okay? Okay, and finally, the third charge, okay, is going to do 9 times 10 to the 9th times 100 times 10 to the negative sixth, okay, over, this is the distance of 1, 2, 3, 4, 5, 5 squared, okay? And then you calculate that out, you're actually going to end up getting 36,000 newtons per coulomb to the left, okay? Because it is positive, again, repulsive. Now, here's the thing to notice, right? Wait a minute, 36 newtons per coulomb to the right, 36 newtons per coulomb to the left. That just cancels out, right? So what's the net field here, right? The net field is just going to be that 90,000 to the left. 90,000 newtons per coulomb left, okay? Okay, couple other things. These are just the last few ones to wrap up here, okay? If a charge of negative 1 millicoulombs were placed at point A, what would the force be on it? Now you could go to the whole trouble of being like, oh, I need to figure out the, you know, what does this one do to A? What does this one do to A? What does that one do to A? But you already got the electric fields. You don't really need it. You can just use Fe equals QE. That's it. That's the easiest way to do it, right? So plug it in. The Q is going to be the charge that you've placed there, negative 1 times 10 to the negative sixth, or sorry, negative third, right? That's millicoulombs, so that would be negative third, okay? And E, the E field, is going to just, the net E field is going to be 90,000, right? Newtons per coulomb to the left, okay? And I'm putting the units here. I didn't put the unit there, right? This is C, coulombs, right? Because I want you to understand that you can see that the units cancel out, okay? So then you end up getting, now you end up getting 90 newtons, okay? But here's the thing, the direction actually doesn't carry over, because if we put a negative there, we have to understand, right, it's a negative charge, so it opposes the electric field. If the electric field's going to the left, then the negative charge is going to want to go to the right. So the force is going to go to the right, okay? Again, we get into that more when we talk about electric fields a little bit later, okay? So if you don't understand that right now, I would say stick with it for a little bit, and then when we get to electric fields, you'll see it a little bit more clearly, okay? The net charge shown on the diagram is this value. Estimate the electric field 30 kilometers away. When we're very far away, when we're far away from a charge, when we're very far away, okay, we can treat all charges as a single combined charge. Okay, so that's going to be E equals KQ net over R squared. Okay, so we'd plug everything in. 9 times 10 to the 9th times 8, or sorry, ooh, why did I write X? I don't even know what I'm thinking right now. Okay, and my whiteout is like dying on me because I use it so much, because I make so many mistakes, not because I'm a bad teacher, okay? 864 times 10 to the negative 6th, okay, over R squared, which is 30,000. Now, why is it 30,000? It's because we had 30 kilometers, right? We convert kilometers to meters, that's 30,000, okay? And then you should end up calculating that out to get about 0.00864 newtons per coulomb, okay? And then in general, when you're really far away from an arrangement of charges, this is just kind of what we did, right? Then you can approximate it as being E equals KQ net, okay, R squared. And Q net is the net charge of the arrangement. Okay, so if you have a bunch of charges in an arrangement, you can take the net charge and figure out what the net charge is, and there you go, that's Q net, okay? All right. There you go. Have fun. That is, what were we just talking about? Electric fields from charges. Electric fields. We just finished talking about electric fields. Okay, have fun. All right. Girl boss gatekeep. Girl boss. Okay.